Alright class, this is day 20 notes, graphing and writing linear inequalities. So this is kind of like what we did last part of the chapter where we graphed just lines, but now we're going to be talking about inequalities. So there's actually more than just the line involved. We're going to be shading portions of the graph that make this solutions true. Our solution set's going to be called the feasible region. And that's the part where the shadings overlap. When you graph, a less than or greater than symbol denotes a dashed line because it doesn't actually exist on the line. And then when you have a less than or equal to, so when you have the equal, you get a solid line because you can equal that line. So let's see what this means. We have plot the following graphs. Now remember, when you see things like this, you don't have to solve for y. You can do standard form. You can do the cover-up method. So for this line here, by the way, this is going to be a solid line. And for this line right here, what I'm going to do is I'm going to let when x equals 0, you get 3y equals 6 or y equals 2. So that's the y-intercept. Put that there. And when y equals 0, you get 2x equals 6 and x equals 3. It doesn't matter that there's an inequality, we're just looking for the points. So now you can see that the slope is down 2 and over 3. So I'm going to just follow that same pattern up 2 and over 3 just to get a more accurate line, because it's not easy to draw on this thing sometimes. Okay, so there it is. Now I'm going to draw a solid line, so like normal. And then we have to shade a certain direction. Now I'm going to just lightly show the direction the shading is. To do that, you plug a test point in. So the easiest test point is 0, 0. So I'm going to test this point to see if it's true or not. So when I test 0, 0, I get that 0 plus 0 is greater than or equal to 6. Okay, which is clearly not true. 0 is greater than or equal to 6 is false. If it's false, that means you do not shade there, you shade the other way. So that means where the truth is above the line. So I'm going to just lightly put lines to show that that is what I'm looking for. Okay. Now we're going to do the other line. This is going to be a dashed line. And then I'm going to do the same method. When x equals 0, y equals -7, and when y equals 0, put a 0 in, you get x is equal to 7 halves. Okay, so that's what, 3.5? And then negative, oh, that's the x though, so I already started that wrong. We have to put that on the x-axis, 3.5, so it's really close to where that one hit. And then the other one's -7 down here. So this is the line. Again, you can kind of estimate at this point, and it's going to be dashed. Do not make it solid because it doesn't equal. Alright, now we have to figure out which way we shade the blue line. So again, I'm going to test 0, 0. If I test 0, 0, I get 0 minus 0 is less than 7. That is true, which means 0, 0 is on the correct side. So this one will shade this way, towards the 0, 0. And then hopefully you guys see that where are both of them shading? They're both shading in this region right here. Oops. So this is the solution area where both of them work. Okay? Because everything down here doesn't work for the green line and everything on this side doesn't work for the blue line. So that is our final solution. Okay? So that's our feasible region. Alright, let's do number 2. X is greater than 2. That is a vertical line. And it is at 2 and it is dashed. So here it is right here. Now for these ones, the test point you can do 0, 0, but just think about it logically. We want x to be bigger than 2. Well, that's this direction. So we're going to shade that way. Okay? Next we have y is less than or equal to 3. That's a horizontal line. This is going to be solid. So I'm going to draw a solid line. And I want it to be lower than 3, so that would be down here. Okay. And finally, we have x plus y equals negative 4. So if you do the zero test, by the way, this is also going to be solid. If you do the zero test, when x equals 0, y equals negative 4. And when y equals 0, x equals negative 4. So I have negative 4, negative 4. So we're here, we're here. So it has a negative 1 slope. I'm going to just put a few dots so I can graph that. And this is also a solid line. And then we have to figure out, just looking at the green line, which way we shade. Well, if you do a test point of 0, 0, is 0 plus 0 greater than negative 4? Yes, it is. So that means the green line shades up towards the 0, 0 point. This is the side that is true. So now you have to look and see where all the shadings overlap. Well, since we have to look at everything to the right of the red line, below the blue line, but above the green line, we have a shading of this region right here. And that will be our feasible region for the problem. Oh, I didn't actually answer the question. So now that we have both regions, let's look down and answer these questions. We have the first question, is the point 5, 1 a solution? So we go over to 5, 1. That's right here. That is outside the feasible region, so we say no. Is the point negative 1, 4? Negative 1, 4 is inside the feasible region, so we'd say yes. For part number 2, is the point 4, 2? 4, 2 is right there. That is a yes. Is 2, 3? Okay, here's where we have to be careful. We're right there. Now, if both lines were solid, it would be true, because solid lines are part of the region. However, you're on the dashed line of x is greater than 2. And since x is not greater than 2 for this point, this is actually no, because you're on the dashed line. So be careful with those. That's just the trickiest part of this. Okay, so that's what we have. That's how you graph those. So the boundaries of the feasible region are used to find the minimum maximum values given an objective function. So your objective function is like your profit or cost that you want to minimize and maximize. If the region is unbounded, as seen above, so both of these are unbounded because they go off forever to the right, like there's not an enclosed shape. And I guess the first one would be unbounded upward. There may not be a minimum or maximum value. Okay, so here's how you do these problems. Once you find your feasible region, you have to test all the points and see what the values are using the given function. So this is our given function. So I'm going to say c is equal to 3 times negative 1. I'm going to use this point for purple, plus 5 times 2. And I get a value of negative 3 plus 10, which is 7. If I do this point, I get c is equal to 3 times 2 plus 5 times 3. That's 6, that's 15, so we have a 21. This one is 6, 0, so 3 times 6 plus 5 times 0, and we get an 18. And finally we have the negative one, c is equal to 3 times negative 2 plus 5 times negative 1, and that's going to equal negative 6, negative 5, negative 11. So once you do all the points, now we have to figure out which one was the min and the max. Well, this is clearly the biggest number, this is clearly the smallest number. So we want the value first. The maximum's a 21, and it's at the point 2, 3. Because that's the point that gave us that maximum for that function. The minimum is going to be negative 11, and that's at the point negative 2, negative 1. Okay. Now we're going to look at this next one. Notice how there's only 2 points, and then this goes off forever. Okay, I know it stops, but technically, since there's no boundary, it will go off forever. So we have c is equal to for this one, 0 plus 5 times 2, which is 10. For this one, we have c is equal to 1 plus 5 times negative 1, which is negative 4. Now, here's where you have to be careful. Let's pick a point way over here in the region. We know that, like, since this line looks horizontal, that like 100, 0 is a point in here. If you do 100, 0 and put that in, you're going to get a c of 100. So hopefully you guys see that this is going to get bigger no matter where you go this way. So because of that, there is no maximum, because the region is unbounded. However, we do have a minimum. We have a smallest point, and it would be negative 4 at the point 1, negative 1. Okay, so if it's unbounded, just think about what it's doing to the function. If it's a max or a min, if it's getting bigger or smaller. Sorry about that interruption. Alright, so now we're going to kind of put everything together. We have our objective function, which is what we're going to test later, but before that we need to get those points. To get those points, we have to graph this region. So this is putting everything together. So I have x is greater than or equal to, so solid. Actually, all these will be solid. Negative 2. So that's a vertical line that's solid at negative 2. And we know that that's going to be bigger because it says x is bigger, so we're going to go this way for the region. Y is greater than negative 1, and that's solid, and it's going to be up here. So right now we're in only this upper right corner region, so we have to just use this third thing and figure out where we're going to go. So x plus y equals 4. Again, when x equals 0, then y equals 4, and vice versa. When y equals 0, x equals 4. Just put 0 in for each and solve. So that means that it hits here and here with a slope of negative 1. I'm going to only graph it up through this region and up down through this region. And it's good to plot points, because at this problem, we need to know what the points are. Okay, so there's that one. So now we basically have to figure out, is it the triangle? Is green shaded down, or is it going to be up and in this region here? Well, it says x plus y is less than 4. So if I do a test point, 0 is less than 4 or equal to 4, that is true, which means we are shading downward, which means that the area region I care about is this triangle region. Okay, and it's not easy for me to fill that in with this highlighter, but so I'll just do, oh, that I was supposed to be on yellow there. Here, I'll do that, even though it's not the highlighter. Okay, so now here's our region. Before you can do anything else, you need to figure out what are these points of the region. Well, we have a point here, and a point here, the corners of your regions where the maxes and mins happen. So I have the point negative 2, negative 1. So negative 2, negative 1, I'll write it over here. I have the point negative 2, positive 6. And I have the point 5, negative 1. So these are the 3 points I have to test using this original C equation. So I'm going to test those down here. C is equal to, I'll do negative 2 and 6. 2 times negative 2 minus 3 times 6. Negative 18, negative 22. I'm going to test this point. Negative 2 times negative 2 minus 3 times negative 1. So that's negative 4, but plus 3 is negative 1. And finally, I'm going to test this point. (10 minus a negative 3, so 10 plus 3 is 13. So we get these values, and the max clearly is 13. The min is clearly negative 22. So the maximum is 13. And again, we will have a max and min because it's bounded, so we don't have to worry about there not being anything. At 5, negative 1, the minimum is negative 22, and that's at negative 2, 6. So that was just putting everything together. We had to come up with our region and then figure out what minimized and maximized our answers. Okay, so the last thing we're going to do is write a system of linear inequalities for real life situations, so we can do these with real life problems. So first we're going to start doing that tomorrow, and that's going to be called linear programming. But here's what you're going to hear in your questions and we can convert them to symbols. And it's basically just kind of thinking about it. So is less than. So if I say x is less than, that usually means it's going like that, because then we'd have x less than something. Greater than would go like that. Less than or equal to is that way. If you hear greater than or equal to, it's that way. Is no more than. Okay, no more than means it can equal it, but we want lower. So is no more than is the same thing as less than or equal to, technically, because we don't want more. We want this to be less than or equal to something. Is no less than is just like is greater than or equal to. Is at most. Again, it means it can only be up to a point, but it could be lower. So it's the same inequality. And this one is at least. So it can be that or more. So those are the symbols you use for those words. So now we're going to go through the situations. Dante is organizing help for a track meet. He needs at least 12 workers. At least. So that means that the number of workers, and it tells you there's T represents number of timers, S represents number of t-shirt sellers. So those are the two types of workers. They also tell you how much they earn and how much they can pay. So let's do the quantity first. We know that the number of workers, timers, plus the number of t-shirt sellers has to be at least. So that means that they have to be bigger than or equal to 12, because then it's at least 12 or more. We also have the cost equation. So this is kind of like what we were doing with the systems. Timers earn 20 an hour, and t-shirt sellers earn $10 an hour. They can pay no more than 220, which means 220 is the most they can pay. So that means that this stuff over here cannot go over that. So that would be less than or equal to. Okay? And that's how you set that one up. Why don't you guys pause the video and try this one here just to see what happens, and then unpause it. So pause. Okay, well, I'm going to keep going. So your work for your uncle's company over spring break to earn some spending money. You spend your time working on two different tasks. So you answering phones and faxes. So X is hours spent answering phones, Y is faxes. You can work no less than 10 hours a week. So we have to do more than 10 hours. So right away, I know that my two jobs have to add up to more than or equal to. It says no less than, which means you can do 10. Now we know $9 for answering the phones, which is X. And you get 15 an hour for sending faxes. That's awesome, actually, because you don't have to talk to people and you can just send faxes and you make a lot more money. Although, who uses faxes anymore? The company says that they pay you at most $200. That means that they can't go over 200. So this stuff has to be lower than 200. So there's our inequality. Okay. Sorry, this video went a little long, a lot of words, but this is linear, or I guess graphing and writing linear inequalities and getting you ready for linear programming.